Alright, so now what we are going to do is we are going to understand how to analyze a system of differential equation qualitatively. Now we did similar sort of a thing in chapter 2 when we have differential equations, right? Remember we had a first order differential equation dy over dx, for example y minus 3. Now we wanted to draw the slope field of this differential equation. So the analog for slope field in the system of differential equations is actually phase portraits. Okay, so let's learn how to draw a rough sketch of a phase portrait and how to analyze it. Now, well, we have to start with a solution. So let me take a simple solution example of a system of differential equation. So this is one of them. And we are only dealing with two-dimensional systems in this lesson. That means we have the two dependent variables x and y. Remember, they are dependent variable. So the solution, for example, given here, capital X means the vector xy, x and y. So if you consider each row of this solution, we can get the solution for x and y with respective. So for example, the solution for x will be the first row, c1 times negative 1 times e to the negative 5t, c2 times e to the negative 7t times e to the t. So that is the first row. So if you consider that first row, you get the solution for x. Now if you consider the second row, we can write c1 times 1 e to the negative 5t plus c2 times 1 times e to the t. So that's the second row. So this is actually the solution for y. So we can get the solution for x and y separately. Okay. Now what we can do is, if you want to plot them, if you want to sketch them, we can draw them on the xt plane here. Okay. And yt plane here, these parametric equations, right? Now, but how about if you want to draw them in the xy plane? So if you draw them on the xy plane, not in xt plane or yt plane, not like drawing these solutions separately, right? Then those two are two planes. How about if we can draw them on xy plane? Then that is a phase portrait, and that is exactly what we are going to do. Okay? Alright, so going back to chapter 2, when we wanted to draw a slope field, there was one important concept. What was that? Finding equilibrium solution. So can someone remember what is equilibrium solution? How do you find equilibrium solutions? Well, what is equilibrium solution means very simple. The solution doesn't change. The rate of change is 0, right? So dy over dx is 0, or we get what kind of slopes? Vertical, horizontal, or what type of slopes? Horizontal slopes, right? There's no change. So we make this equal to 0 because dy over dx is 0, no change. So you get equilibrium solution at y is equal to 3 here, for example. So equilibrium solutions or equilibrium points is such a key thing when we were drawing the slope field. Here in the phase portrait, it's also the same. But what is an equilibrium point in a phase portrait or in a system of differential equation? Well, it turns out it's very easy. Now in this lesson, we are only dealing with homogeneous system of differential equations. Okay, so far we only learned that. Now let's build up an example by ourselves. Dx over dt is 2x plus 3y. dy over dt is negative 3x plus 2y. Now these are two equations. Now if you want to find the equilibrium point, you want to make this equal to 0. Both of them have to be equal to 0. Now what is the point, xy point, where you have rate of change 0? That is, tell me an x and y value that satisfy both of these equations, that makes these two left hand sides 0. What is x and y value? What is a guaranteed x and y value that you can just see by looking at these two equations? 0, 0, right? When x is equal to 0 and when y is equal to 0, it is guaranteed to be an equilibrium point of a system of differential equation, not just a random system, a homogeneous 2 by 2 system of differential equation. Okay? So 0, 0 is always an equilibrium point. So you have to remember that throughout the lessons, okay, since we until we are dealing with homogeneous systems. Okay, all right, so that's an important factor. Now we have to invent few things more. Now, what do we use when we want to write a solution, or we want to construct a solution of a system of differential equations? What we do is, step by step, we find the eigenvalues, we find the eigenvectors, then depends on the eigenvalues you write the solution, right? So far we only discussed what do we do when we have distinct eigenvalues, distinct real eigenvalues. So what you do is you just simply take the linear combination of them. We have a way to write them, right? You know that already. So I guess there should be a major effect coming from eigenvalues and eigenvectors when we are drawing the phase portrait, right? Definitely yes. So the shape of the phase portrait, or the trajectories, or I should say the trajectories means the solution curves. So in this lesson, the solution curves for different arbitrary constant, the solution curves, we say them trajectories. Okay, so there are three cases. So in this case, in this lesson, we are dealing with distinct eigenvalues, right? Distinct real eigenvalues, lambda 1 and lambda 2. The first case is, how about if both of them are positive? The second case is, how about if both of them are negative? The third case is, how about one is positive and the other one is negative? The order doesn't matter here, okay? Maybe lambda 2 is positive, lambda 1 is negative, that doesn't matter. But this is a mixed of sign. Here both of them are negative, here both of them are positive. What type of phase portraits we get, what type of behavior we get? So we have three cases. We have to understand and learn these three cases separately. That is what we are going to do in the next video. Okay, so this is just an introduction for phase portraits. See you in the next video. Thank you.